Welcome to Aviation Weather Training for Air Traffic Controllers. This lesson will teach you the characteristics of thunderstorms and their effects on aviation. After completion of this course, you should be able to identify the ingredients for a thunderstorm, the stages of the thunderstorm, types of thunderstorms, thunderstorm hazards to aviation, methods for avoiding thunderstorms in flight, and the tools and products that we use to monitor and forecast thunderstorm activity. First, a quick review. Thunderstorm cell formation requires the following three ingredients: sufficient water vapor, unstable air, and a source of lift or a mechanism strong enough to release the instability. One or two of these ingredients may be present, but without the third in sufficient quantity, you may not get a thunderstorm. Where do we get these ingredients? Well, for moisture, the major sources over North America include the Atlantic and Pacific Oceans, as well as the Gulf of Mexico. In the Minneapolis region, the Great Lakes may also assist in development by providing moisture and producing lake breezes and lift mostly over land. During the spring and early summer, the Great Lakes temperature often actually suppresses surface-based thunderstorm activity. The second ingredient, instability, air is considered unstable if it continues to rise when given a nudge upward. The characteristics of an unstable air mass is warm moist air near the surface with colder and drier air aloft. And moisture actually adds to instability. Energy is released through the condensation process as you lift that warm moist air into a colder and drier air regime. And the more moisture you have, the faster it can climb. Finally, there needs to be a mechanism to initiate the upward motion. These can include uneven heating of the lower layers from solar and terrestrial radiation, fronts, dry lines, and outflow boundaries, which actually act as wedges to lift warm and moist unstable air to saturation and produce a cloud and the eventual thunderstorm, and terrain. And thunderstorms all have life cycles. A thunderstorm cell undergoes three distinct stages during its life cycle: the towering cumulus stage, the mature stage, where you have significant updrafts and downdrafts occurring side by side, and then the dissipating stage, where the precipitation tapers off and ends. And what makes dealing with thunderstorms tricky is that a thunderstorm may go through all three stages in as little as 30 minutes or last for hours. In the cumulus stage, a cumulus cloud begins to grow vertically, perhaps to a height of 20,000 feet, before initiating precipitation and developing ice in the cloud. The initial updrafts in a cumulus cloud may be as high as 3,000 feet per minute. And the cloud edges are sharp, and building and expanding may actually be seen with the naked eye. In the second stage, the mature stage, a storm has reached a considerable height, often 40 to 60,000 feet. The icy cirrus anvil top appears, and the rain shaft at the bottom. Strong updrafts up to 6,000 feet per minute could exist, and downdrafts. And this is the most dangerous stage when large hail, damaging winds, icing, turbulence, and lightning are all present. In the dissipating stage, the downdraft has cut off the updraft, and the storm no longer has a source of warm moist air to sustain itself. The cloud takes on a fuzzy appearance, but you may have some light rain and weak outflow winds. Now for the different types of thunderstorms. There are three different types we'd like you to know. The first type is the single cell, which consists of a single main updraft that is quickly replaced by a downdraft once the precipitation begins. These are short-lived. They may last only about 30 minutes. They're easily avoided by pilots except at night or when embedded, and they're sometimes referred to as pulse, popcorn, or air mass thunderstorms in the absence of strong fronts. Most frequently, they occur in the Minneapolis region during the late summer in the absence of fronts, but you do have very moist tropical air present. The hard part of dealing with single cells from an aviation perspective is that the precise locations of isolated air mass development are hard to predict. The second type, the multi-cell storms, they usually occur along a front or an outflow boundary. Individual cells mature and are carried downstream by the upper winds, and new cells then form upwind from the previous cells and take their place. This shows why cell movement may often be different than area or line movement. The cell moves forward, but the actual area of development is shifting more slowly. So when someone asks, how fast are those thunderstorms moving? The answer can often be given in two different ways. A classic example of this is the training echoes example. When the lifting process is shifting very slowly or stationary, training echoes may occur. Each of the thunderstorms follow the path of the preceding storm. The cells move, but the area does not. This can create large rainfall amounts over a short period in a small area, which may lead to flash flooding. But it's also tough on air traffic management, particularly if a line of thunderstorms forms over a major route or an approach to an airport. Multicells may also develop as squall lines. When the area of lift is shifting rapidly, thunderstorms may form in a line which can extend laterally for hundreds of miles. These squall lines can persist and move for many hours and produce damaging winds and hail. Gust fronts or damaging straight-line winds are common, and the multi-cell squall line type thunderstorm is most common in Minneapolis during the late spring and early summer months when you have very dynamic frontal activity. The third type of thunderstorm is the supercell. This is the main source of severe weather. Updraft speeds can exceed 9,000 feet per minute, and multi-cell clusters and lines may also have supercells incorporated as part of their system. What defines a supercell? Well, a supercell occurs when your instability and lift is so strong that the cell develops its own rotating mesoscale circulation, sort of like a miniature low-pressure system. The rotation of the storm may actually be visible. This results in extreme wind shears and extensive turbulence and very high tops, often in excess of 45,000 feet. Thunderstorm hazards can actually be found with any thunderstorm, not just the supercell type. And these include hail, low-level wind shear in the form of microbursts or gust fronts, lightning, icing, and turbulence. The first hazard, hail, is associated with sustained updrafts in the front part of a thunderstorm, most frequently with multi-cell or supercell type storms. It can often be found aloft but not at the surface, and can be encountered in clear air several miles from thunderstorm clouds, such as under blow-off or anvil tops. The next hazard, low-level wind shear, is an abrupt change in wind direction and/or speed that occurs in low altitudes. It is important to note that abrupt wind shear can occur at any altitude, but it is most dangerous near the surface where there is little room for operational error. The definition of low-level wind shear is a change of wind speed of 10 knots or more per 100 feet in a layer more than 200 feet thick, which occurs within 2,000 feet of the surface. The definition of severe low-level wind shear is an airspeed loss or gain of at least 15 knots and/or altitude loss of 500 feet per minute. The main issue with low-level wind shear is its effect on aircraft performance, when this effect occurs close to the ground. While an aircraft is on approach, a shear from a headwind to a tailwind causes the airspeed to decrease, the nose to pitch down, the aircraft to drop below the glide slope, and resulting in undershooting of the runway on approach. Conversely, if there is a slight tailwind and the flow shears into a headwind, this causes the airspeed to increase, the nose to pitch up, the aircraft to balloon upward above the glide slope, and overshooting on the runway on the approach occurs. With a thunderstorm, wind shear is usually found in two forms, either a microburst or a gust front. A microburst is a downburst that covers an area of less than 2.5 miles along the side with peak winds as high as 170 miles per hour that last 2 to 5 minutes. It's an area of diverging winds at or near the surface. The main point to be remembered about microburst activity is that the strong wind shears associated with a microburst are often non-recoverable and can result in serious aircraft accidents. Let's look at what happens when an aircraft attempts to land in a microburst. At point X, an airplane enters the microburst zone where a headwind causes it to balloon above the normal glide slope. At the center of the microburst, at point Y, there is a downdraft which causes the airplane to sink. At point Z, the airplane enters the most lethal zone where a sudden tailwind causes the airplane to lose airspeed. In a gust front, a gust front is the leading edge of a cool air rushing down and out from a thunderstorm. The edge of a gust front is known as an outflow boundary. The abrupt wind shift may actually occur miles away from the parent cell, not necessarily under the thunderstorm. A gust front is actually an area of converging winds at or near the surface, and you can see the echoes from a gust front on Doppler radar. Wind shears are usually less critical than in a microburst, but it still may be a zone of severe turbulence and cause overshooting of the runway. The next thunderstorm hazard, lightning, typically doesn't cause damage because the current is directed along the outside skin of an aircraft. If there is damage, it usually is minor and might include outside punctures, electronics, or damage to the navigational equipment. An important point to remember about lightning damage is that airlines must inspect the aircraft after any lightning strike, and this will cause flight delays with or without damage, which can run into dollars. The next hazard, icing, occurs where you have abundant supercooled liquid water droplets, and a thunderstorm contains many of these. Mostly occurs between 0 degrees Celsius and minus 15 degrees Celsius. The SLD, or the supercooled liquid water droplets, freeze on impact with an aircraft. Clear icing accumulation may be very rapid with SLD present. At high levels in a thunderstorm, icing from smaller droplets may be rime or mixed rime and clear. Finally, the last thunderstorm hazard, turbulence, occurs within the cloud due to shear between updrafts and downdrafts, but severe turbulence associated with a thunderstorm can also occur above, near, and downwind of cells. And on the left, here's an example of blow-off turbulence over the central United States, including part of the Minneapolis region due to a large thunderstorm complex. What we're seeing here are 3 different aircraft, each flying along the periphery of a thunderstorm, but they're all reporting turbulence, at least moderate turbulence, with a couple reporting moderate to severe turbulence. In general, pilots are told to avoid the inside of a cell, obviously, but also flying directly above thunderstorms, especially developing cells and the downwind areas. A typical rule of thumb for avoidance distance is about 1 mile for every 1 knot of wind at flight level. So if you have a 60-mile-an-hour wind at the flight level, they're told to avoid the downwind area of a thunderstorm, avoid the actual cell by at least 60 miles. On other sides, the area within 5 miles of a cell is to be avoided, and that's sometimes a greater distance depending upon the altitude and existing pilot reports. Now, how do we follow the thunderstorm development and movement? Well, there are 2 different types of products. There's real-time products and there's forecast products. Real-time products give users awareness of thunderstorms and related events as they occur, while forecast products provide a glimpse of thunderstorm characteristics in the future. Let's first look at real-time products. The FAA has installed the following systems to warn terminal controllers and pilots of microbursts, wind shears, and gust fronts. There's LWAS, or the Low-Level Wind Shear Alert System, with up to 32 remote wind sensors situated around an airport. There's also the Terminal Doppler Weather Radar, or TDWR, which is a specialized weather radar used to detect microbursts, gust fronts, and convective storms. This radar updates more frequently, every minute, and scans lower than the National Weather Service NEXRAD radar. There's also the Airport Surveillance Radar with its weather system processor. And it's an enhanced weather processor for ASR-9 air traffic control radar that includes a Doppler wind estimation capability. The output from these different systems are relayed to the tower and then relayed by voice to pilots that are on approach or departure. The next system is the warp system that you're familiar with. The weather radar processor, WARP, takes radar data from the NEXRAD sites and overlays it on a controller's scope. The limitations on WARP include the fact that it only displays precipitation in 3 levels: moderate, heavy, and extreme. The radar data is also typically 1 to 6 minutes old when it appears on a controller's scope. Individual NEXRAD sites will update at different times. The sites are not necessarily synchronized, and cloud boundaries and turbulence are also not displayed. The controller DSR presets also do not include weather radar display preferences. CWS is short for the Corridor Integrated Weather System, and this is used to observe and forecast precipitation activity out to 2 hours in advance over highly traveled, high-impact areas of the NAS. It is a mosaic of NEXRAD reflectivity radar with tops and movement info and navigation overlays. It has an algorithm to forecast future locations out to 2 hours. However, this is a mathematical algorithm and will often not represent development and weakening trends. This is available in the CWSU, in the TMU, and all control areas. ITWS stands for Integrated Terminal Weather System. It's used to observe and forecast local thunderstorms using the local output from the TDWR. It also may integrate other data sources, including LWAS and adjoining radars. It will depict microburst gust front locations and movement, and is a pretty valuable tool when dealing with approach and departures. This radar is available in the TMU and the CWSU. In the CWSU, we issue the Center Weather Advisory. It can be issued anytime, and it's valid up to 2 hours. It can be issued for isolated thunderstorm activity. For thunderstorms, the CWA is usually valid until a convective signet is issued, which covers the same area, unless more detail is considered important by the CWSU or the activity remains isolated and below signet criteria. And one important point about this is that location and effect on traffic is also important. Isolated thunderstorms may not be covered by a CWA if the thunderstorm is in a remote area. Available on the aviationweather.gov page or ads page are the following tools. The first is the convective signet. Convective signets are issued at 55 minutes past the hour by AWC and are valued for 2 hours. They typically focus on either severe or broken thunderstorm activity. And any convective signet implies severe or greater turbulence, severe icing, or low-level wind shear. Also available on the aviationweather.gov site is the CCFP. It's short for Collaborative Convective Forecast Product. It's a strategic forecast of convection used to guide traffic managers in their system-wide approach to managing traffic. It's not intended for tactical use. It's a collaborative forecast that is put out by the Aviation Weather Center, CWSUs, and the airlines, and we do participate in this. It shows coverage, confidence level, tops, and projected movement of areas. It basically consists of three forecast maps with lead times out to 4 to 6 and 8 hours, and is updated every 2 hours. Here's a key to the CCFP. It's important to remember the coverage is indicated by patterns, and the confidence levels are indicated via the color of a polygon, where low confidence is in gray and high confidence in the forecast is in blue. Final graphic that's available on the ad site is the PIREPS graphic, and this may contain information regarding winds, turbulence, icing, clouds, and precipitation that are caused by thunderstorm activity. Of course, these are passed along by you, and there are some tips to remember in producing a PIREP. Remember that low-level wind shear, a report of hail, severe icing, moderate to severe or even extreme turbulence are all urgent PIREPs. Also, the tops in a PIREP usually refer to cloud tops, and they are not going to match the radar top information. So that brings us to our final point, which is a plug for more PIREPs. It's important to remember that PIREPs are not just for the CWSU. They're for the entire aviation community. Forecasting and flight planning are 24-hour operations. Day or night, there are people that want to know what is being experienced out there. And the only way to know for sure is through pilot report information. Confirming that there is no hazard is often as important as indicating that there is a hazard. For example, knowing the smooth altitudes are as important as knowing where there is turbulence. And details give flight crews, airline dispatchers, and aviation weather forecasters valuable insight into what's going on. Winds and temperatures are incorporated into models, and it's important that the locations and times of the report be included every time. And finally, we thank you for this information. So in summary, here are the topics we have covered, and this concludes the Spring 2014 Weather Briefing. Thanks for your attention.